All right, guys, before we go on, I want to go ahead and do a few more of the equations and talk a little bit more about naming. For example, let's take a look at this one. And so if you're looking through your list, let's say Ag NO3 plus Cu NO3 2 plus Ag. Right, so there's the equation. This is a single replacement. You guys can see that. And I don't know if you remember, but single replacements are also always redox equations. Always something is going to get reduced. Means the oxidation number will lower and will gain electrons. And the oxidized will gain an will go higher oxidation number and will lose electrons. And I know that part confuses people often because you got to remember that the oxidation number is the same as the charge. So if you have become a lower oxidation number, you have a more negative charge. You have to have gained electrons. If you're oxidized and you have a higher oxidation number, that meant you had a positive charge, and so you had to lose electrons. So if you're looking at this to balance, let's see, since the NO3, the nitrate on this side and the nitrate on this side haven't broken down, we can sort of treat that as one thing. So if you notice over here we have 2 nitrates, that means we need to, over here, put 2 on the silver nitrate. Remember, silver does not need an oxidation number, so we could just call this silver nitrate plus copper. On this side, now let's see, we need to put a 2 in front of our silver. But now copper, this copper must have an oxidation number. If we think about it, cross that back up. This is a oxidation number of +2. This missing number, remember, is a 1, so this would be -1. So this would be copper 2 nitrate. Silver, zinc, aluminum don't need one, but the rest of our transition metals do. And so that's balanced. It's a single replacement. We could say, let's go ahead and identify the oxidation numbers. We've got copper here and nitrate. Let's go ahead and put the other nitrate. Remember, the first rule is any element by itself has an oxidation number of 0. Whether it's diatomic or not, these aren't, but they're both 0. And if we add up the oxidation numbers, they have to equal 0. So if this nitrate is a -1, that must mean this guy is a +1. So now we have all of the elements identified. We haven't broken this down, and I'm going to show you how to do that in a second. Let's just go ahead. Because the nitrate stayed the same on both sides, we know that neither nitrogen or oxygen was reduced or oxidized. The whole thing stayed the same. So silver started as +1, ended at 0. It reduced, went from +1 to 0. Silver reduced. Copper went from 0 to +2. It oxidized. The silver, the 2 silvers had lost 1 electron each. The copper here, that's just the one of them, gained 2. All right. So moving on, let's take a look. I think we're going to go ahead and flip to the next page. And let's see, we're going to look at, oh, I'm out of order here, guys. Let's see. We did that. We're here. Okay, and we did these on the other sheet, and I'm using 2 copies, and so I keep losing my other copies. But we did these. Remember, we talked about the single replacement equation reactions. Those you always look at your electronegativity chart. If the electronegativity difference increases, we're good. If the difference increases, then the reaction happens. All right. For the double replacement reactions, they almost all take place in a solution, so we have to use the solubility rules. And we should have something that's a soluble plus a soluble gives you a soluble plus a precipitate. That's the solid bit that falls out. So we did our neutralization reactions. Let's move on and let's look at some more redox, and that's what we were just talking about a second ago. So what is oxidation? It is a loss or losing electrons. We gain a higher oxidation number. What is reduction? We're going to gain electrons. So let's write, I'm going to write more positive up here. I think that's a little bit clearer. Gain electrons, lower ox number, or think about it more negative. Okay, so for each equation, we are going to identify what is oxidized, what is reduced, and identify the oxidizing agent, reducing agent. Remember, what is oxidized is the reducing agent. What is reduced is the oxidizing agent. So once again, I know this is really small, so we are going to grab this extra sheet of paper, and you guys can follow along on your sheet. This first one is a combustion reaction, and if you notice, it's already balanced. And so we've got some carbon, some hydrogen, some oxygen, and we combust the methane. You guys should be able to name this C. There's one, so the prefix is methane, C4. All right, plus some diatomic oxygen gives us water and carbon dioxide. So remember, first rule, element by itself. So O2, carbon, iron, the ox number is 0. Second rule, let's give group 1 equals plus 1 when it's in an atom. Group 2 equals plus 2. Let's go ahead and add aluminum, plus 3. Zinc, plus 2. Silver, plus 1. How about a third rule? The sum of a molecule ox numbers equals 0. Right? Fourth rule, sum of a polyatomic ion ox numbers equals the charge of the ion. Oops, charge of ion. All right, fifth, and I write these in different orders. There's no real number associated with it. You just need to know all these different rules. Oxygen in its normal state, oxygen is -2. And let's go ahead and throw in hydrogen in its normal state is +1. I may remember some more rules as we're going along, but these are really good to get you started. And so let's go back to our our equation and let's see what we can get. So things like carbon. Carbon is usually a +4 or a -4. He's right in the middle. He can get a little tricky, but let's take a look and see what we've got. Let's start with oxygens, because if we're looking at that, he's a -2. He's a 0. Why is that oxygen a 0 instead of a -2? Because he's by himself. In the first rule, elements by themselves are 0. Doesn't matter that he's diatomic, doesn't matter that there's 2 of them, he's still 0. So right now you could see that in this case, that oxygen reduced 0 to -2. If we look at carbon dioxide, also -2. So we know oxygen reduced. Okay. Let's look. Hydrogen, normal state, +1. Still +1 over here. Let's see. That means if he's a +1, this carbon has to be acting like a -4. Does that make sense? He's a +1, and there's 4 of him. So we got to balance. The +1 times 4 equals -4 times, remember there's no number, that's a 1. So that's balanced. -4 times 1 is the opposite negative balance to this +4. -2 times 1 opposite to +1 times 2. -2 times 2. That's -4. There's only one carbon. This carbon now has to be acting like a +4. So if we look at this, oxygen reduced carbon oxidized. So now you can go back to your sheet, and on that very first we can say, oops, sorry, hold on.
Miss Overly, could you please stop by the main office? Miss Overly, please stop by the main office.
Oxidized, we said that was the carbon. Reduced, we said that was the oxygen. Ox agent, that must be the oxygen. Reducing agent, that would have been the carbon. All right, let's do one more example of this. And we've got another one that we can do. Oh, let's see. I think I'm going to look at the next one. Al2O3. It's 2 of those. Plus 3C, carbon by itself, goes to 4 aluminums plus 3 CO2. Watch the typo, the subscript should be dropped. So what's happening? This looks like a single replacement where carbon comes along and kicks off aluminum. Now, that is one of those reactions. If you go back to your electronegativity rules, you'll see this is probably not going to happen. However, if it did, we can take a look and let's check if we're balanced. We have 4 aluminums, 2 times 2, 4 aluminums. 2 times 3, that's 6 oxygens. 3 times 2, 6 oxygens. 3 carbons, 3 carbons. So we're balanced. Now we're going to use our rules and determine our oxidation numbers. Anything by itself, like the carbon or the aluminum, we're going to call a 0. Oxygens, let's go ahead. Oxygen's in its normal state, -2. Oxygen in its normal state, -2. Now we're going to use the rule that I said that the molecule's total sum needs to be equal to 0. So -2, but there's 3 of them, so -2 times 3, that gives me 6. That means I need to put that 3 up here and think about that as a +3. +3 times 2 equals 6, and so those two will cancel out, the -3 and the -6 and +6. So we're good, that equals 0. If we look over the carbon dioxide, we've already done carbon dioxide in our last example. -2 times 2, that's 4. So 1 times +4 equals 4. So now we're balanced. So what happened? Aluminum reduced from +3 to 0. Aluminum reduced. Carbon oxidized from 0 to +4. Carbon. In a double replacement where what's replaced is the cation, the positively charged ion, the one being replaced, the aluminum being replaced, always is reduced. The one doing the replacing is always oxidized. So, and we can flip, so if aluminum is reduced, aluminum is our oxidizing agent. And if carbon is oxidized, then carbon is our reducing agent. All right, and so there's a few more examples. I would really encourage you guys to try those yourself. Go back to the rules if you get stuck. I'm going to show you one more example, in which case that we're going to break up a polyatomic ion before we move on. And I will show you that in a second here, and then next video we will talk about the rest. So let's take a look at a different equation. So we need something where our polyatomic ion breaks up. We need a decomposition reaction, or we need something else like that where we take a polyatomic ion and we break it into pieces. So I'm looking for one. How about, here's a good one. KClO3. All right. Okay, so if you guys can all see this, this is a decomposition reaction. And it's a decomposition reaction for potassium chlorate to potassium chloride and oxygen. Remember, our chlorates always decompose to a salt and an oxide. So, potassium is a group 1. Actually, let's start with our element by itself. Remember, that's always our first rule, so that guy gets a 0. Group 1s always get a +1. All right, so let's look at this guy. +1 and the Cl all by itself. To balance that +1, I guess we need a -1. We can't just look at this chlorine all by itself because we see that, you guys can see that the potassium hasn't changed, so it neither reduced nor oxidized. We're going to actually have to break up this polyatomic ion and see what is the Cl contributing and what is the O3. So let's break that up. I'm going to take this guy and I'm going to expand him. ClO3. Altogether, he needs to equal -1. My oxygen is -2. So together, this guy, he's a -6. All right, makes sense? -2 times 3, -6. I have to balance that to get it not to 0 because we're not an atom, we're an ion. I need to make whatever carbon is plus him equal a -1. That's the charge of the chlorate. -1 is the charge of the chlorate. So the chlorine plus the oxygen has to equal the chlorate's charge. So chlorine has to be, if oxygen is a -2 and there's 3 of them, making it a -6, chlorine has to be, in this case, he is a +5. +5 plus -6 equals -1. So if I go back up here, my oxygen's a -2 and my chlorine is a +5. So let's see what happened. Chlorine went from +5 to -1. Chlorine +5 to -1 reduced. Oxygen went from -2 to 0. Oxygen oxidized. And that one's a little trickier, and the only time you have to do that extra step is when your polyatomic ion either is formed or breaks up. So in other words, the polyatomic ion is not found on both sides of your equation. In double replacements, where it just switches, you don't need to break it up. You can just look at it as a whole. Hopefully that makes sense, and I will talk to you guys in the next video.